Hello, and welcome to Mr. Rising's Math Learning channel. Today's video, in our probability unit, we'll be talking about factorials. They are so exciting, they even have an exclamation point. Okay, maybe they don't seem that exciting right now, but as you'll see, they are quite easy to work with and they make a lot of intuitive sense whenever you're working with probability. To start, let's take a look at the definition. The definition says the factorial of a positive integer n, those are numbers 1, 2, 3, 4, and so on, any whole numbers, is the product of all the integers from 1 to n, the product. And we denote n factorial as n exclamation point. So, writing out n factorial, we know that this is a product, and product means multiplication. We are multiplying all the integers from 1 to n. So that would look like 1 times 2 times 3 times all the numbers all the way up to n minus 2, n minus 1, times n. This is the product of all of the integers from 1 up to n. Now that we have a formula that we can write out a factorial as a product, we can go ahead and take a look at a few numerical examples. Let's take a look at 4 factorial. 4 factorial would be the product of all the integers from 1 up to the number 4. So that would look like 1 times 2 times 3 times 4. Multiplying these together, we see that 1 times 2 is 2, times 3 is 6, times 4 makes 24. So our answer for 4 factorial is 24. Another example would be 3 factorial. To write out 3 factorial, it would just be all the integers from 1 to 3 multiplied together. So 1 times 2 times 3, that would give us 6. And similarly, with 2 factorial, even easier, just the product of all the integers from 1 to 2, which would just give us 2. Some larger examples, say 7 factorial, are just as easy to compute, but they can be time consuming, so they're a lot easier to just enter into a calculator. 7 factorial we could write out as the product of 1 times 2 times 3 times 4 times 5 times 6 times 7. And if we multiply all those guys together, we get 5,040. As you can see, as we move up through the integers, these factorials are getting pretty big pretty fast. If we take a look at 13 factorial, these numbers get so huge so fast that 13 factorial is equal to 6,227,020,800. How unlucky of us to have to deal with numbers that big. But, fortunately for us, more often than not, we see factorials in rational expressions rather than on their own. In rational expressions, a lot of these factors of the factorials, the individual integers that are being multiplied together, will cancel out, which makes the numbers a lot smaller than what we're dealing with whenever we see 13 factorial. Looking at factorials in rational expressions, we'll go ahead and start by looking at some numerical examples. We'll take a look at 5 factorial over 3 factorial. This might look daunting because we have two factorials in the same problem, but remembering what our definition of a factorial is, 5 factorial is just the product of 5 times 4 times 3 times 2 times 1. All of the integers from 1 up to 5. And then the denominator will just be 3 factorial, which would be 3 times 2 times 1. Now notice, conveniently for us, these share a lot of the same factors, and so they'll cancel out. The 3, 2, and 1 will cancel because they are in both the numerator and denominator. And that just leaves us with 5 times 4. And 5 times 4 is 20. When dealing with larger factorials, it may be more convenient to write the product of the integers 1 through that number in a different way. For example, if we looked at 14 factorial over 12 factorial, a lot of terms are going to cancel out, but do we necessarily want to write them all out? That's the question. So, taking a look at this, I could write out 14 factorial as a product of 14 times 13 times 12 times 11 times ... all the way to 3 times 2 times 1. But, notice, I could go ahead and write it as 14 times 13 factorial. Because isn't this right here, this product of 1 through 13 factorial? So we have the product of 4 times 13 factorial, or we could even write it as 14 times 13 times 12 factorial. And that works out very conveniently for us whenever we can write this fraction out up top as now 14 times 13 times 12 factorial all over 12 factorial. The 12 factorials will then cancel out. And that leaves us with 14 times 13, which is equivalent to 182. Anytime we have a rational expression with factorials in it, like we did here, we can always take the larger of the factorials and expand it as a product of some factors times the other factorial. And the convenient thing about that is that the other factorial, the smaller factorial, will cancel out, leaving just a product of factors. In this case here, we expanded 14 factorial to be 14 times 13 times 12 factorial. If we wanted to try this again with, say, 5 factorial over 7 factorial, we would expand the larger one. So we would have 5 factorial over 7 times 6 times 5, and we would cut it off there, 5 factorial, because that's what we want to get rid of from our expression. So the 5 factorials would cancel out, and we have 1 over 7 times 6, which is 1 over 42. Taking some of the same tricks that we used whenever we were simplifying numerical examples of rational expressions of factorials, we could go ahead and apply those to factorials with integer variables. Take, for example, the rational expression n minus 1 factorial divided by n plus 1 factorial. How would we go ahead and simplify that? Well, we could go ahead and take a look at the definition of what a factorial is. The definition of a factorial for n minus 1 factorial, we could go ahead and write that out as the product of 1 times 2 times 3 times all of the integers all the way up to n minus 1. The numbers preceding n minus 1 would be successively 1 less, So 1 less than n minus 1 would be n minus 2. 1 less than that would be n minus 3, and so on. In the denominator of our expression, we'd go ahead and do the same thing. We've got the product of all the integers 1 times 2 times 3, all the way up to n plus 1. The numbers preceding that would be successively 1 less also, because this is the product of all the integers from 1 up to n plus 1. So 1 less than n plus 1 would be n, and 1 less than that would be n minus 1, and so on. So we notice that, like any other case that we've had with rational expressions of factorials, that a lot of these factors cancel. The n minus 1 factor cancels, n minus 2 would cancel, and so on, all the way down to 1, leaving us with just 1 over n times n plus 1. But, using the same trick from last time, we could go ahead and identify that the n plus 1 on the bottom must be bigger than n minus 1 in the numerator. Because n plus 1 is bigger, we could go ahead and expand that out until we get the factors to match up. So we could write out n plus 1 factorial as n plus 1 times n minus 1 factorial. And on the top, the numerator, we still have n minus 1 factorial. Conveniently, the n minus 1 factorials cancel out, and we are left with, again, 1 over n times n plus 1. The takeaways from today's video are that n factorial is simply the product of the integers 1 through n. For example, 3 factorial is equal to the product of 1 times 2 times 3. And also, simplifying expressions with factorials can be made easier by canceling out terms and only writing out as many terms as are needed. For example, 3 factorial over 2 factorial is equivalent to 1 times 2 times 3 over 1 times 2. There's a lot of canceling that happens. The 1's cancel, the 2's cancel. We're left with just 3. But an even simpler way we could do that is we could rewrite 3 factorial over 2 factorial, expanding out the 3 factorial into 3 times 2 factorial. And so the 2 factorials then cancel, and we are left with also 3. As we move on, we'll be using these a lot whenever we use permutations and combinations, which are very common in the theory of probability. Thank you very much for watching this video, and come back and learn another time.